Welcome to the Logger Lecture Series, named after McMaster graduate Albert Abram Logger, a great believer in the value of lifelong education. He created the Albert Abram Logger Foundation, which supports several organizations in their efforts, including the McMaster Alumni Association. The United Nations 17 Sustainable Development Goals, SDGs, are a call to action to end poverty and hunger, protect the planet, and ensure healthy lives, peace, and prosperity by the year 2030. At McMaster, we recognize our responsibility to address these goals as we work together across disciplines and faculties, locally and globally, to create a healthier, brighter world. In 2022, our online Logger Lecture Series will feature talks by McMaster researchers, projects, groups, and alumni to showcase how McMaster is helping to reach these goals. Today is the United Nations World Water Day. Since 1993, people and organizations mark World Water Day by taking action to tackle the global water crisis.
Good evening and welcome to McMaster Alumni Association and McMaster Center for Climate Change public lecture entitled Discovering the Deep, Life in Our Lost Wilderness. My name is Altaf Oren, and I have the privilege of serving as the director for the McMaster Center for Climate Change and hosting tonight's talk in collaboration with McMaster Alumni Engagement Office. One of our main focus of the center is science communication and community outreach. We are proud to host today's talk by an internationally renowned scientist. This talk is coinciding with the World Water Day today. Tonight's talk has drawn about 400 participants. We are recording the talk so that you can share it with family and friends and colleagues. Tonight, we will be hearing from distinguished ocean scientist, Dr. Verena Tunnicliffe. After Dr. Verena's talk, you will have the opportunity to ask questions. Please type your questions in QA box on your screen. We'll try to cover as many questions as we can. To introduce Dr. Verena, I would like to invite the Dean Faculty of Science, Dr. Maureen McDonald. Maureen is the first woman to serve as Dean for the Faculty of Science. In addition to leading Faculty of Science with more than 8,000 students and 300 faculty and staff members, Maureen also runs a research lab in the Department of Kinesiology. She has been nationally recognized for her excellence in student mentorship. Maureen?
Thank you so much, Altaf, and good evening, everyone. This is our second event today in the Faculty of Science to mark World Water Day. Earlier today, 3 students connected to the Faculty of Science organized a conference that featured keynote speakers by a senior fellow from the United Nations University, an Ojibwe elder, and an Indigenous legal scholar. Tonight, we're going to begin our talk the same way that we began that conference earlier today, with a land acknowledgement. I know that we showed you a screen earlier, but I'm going to emphasize some of the language in that screen and talk about what it means to us at McMaster University. Doing these land acknowledgements is an opportunity for us to show respect for Indigenous peoples and their enduring connection with the traditional territories, but also with their history with this land and now together with us. We are guests on the territory where we currently have the privilege to study, work, and live. And I know that many of you are connecting from areas distant from McMaster University. Wherever you are, it's important to acknowledge the original inhabitants of the lands and the history they share with the land, as that is one quite important step, but not the only step towards reconciliation. At McMaster University and in the Faculty of Science, we are committed to many principles, and front and center on those are our principles related to equity, diversity, and inclusion, as well as indigeneity. In these principles, we hope to then translate them to an environment where all our stakeholders are aware of and serious about reconciliation. Me giving this land acknowledgement today at the beginning of this important lecture is one step towards reconciliation, and it's important, again, for us to recognize it's only one step. The traditional territories where McMaster University is located are traditional lands of the Mississauga and Haudenosaunee nations, and are within the lands protected by the Dish with One Spoon Wampum Agreement. In that agreement, the wampum provides a symbolism for a dish that represents the territory, and the spoon represents that the people are to share the resources of the land and only take what they need. For many thousands of years, the first people sought to walk gently on this land, offering their assistance to the first European travelers and sharing their knowledge for survival in what was, at times, a very harsh climate. As a descendant of those European settlers, I acknowledge how important it is for us to seek new relationships with the original peoples of the land, and that relationship to be based in honor and deep respect. I hope as you engage with this wonderful lecture this evening, you be guided by and embrace thoughts of right action and love as we look to transform our personal and institutional relationships with our Indigenous friends, neighbors, and colleagues. And now I'm going to transition to introducing our remarkable speaker this evening. Dr. Verena Tunnicliffe is a scientist, a deep sea pioneer, and a marine biologist. I get to do a lot of introductions every year, but it's not very often that I get to do an introduction of a female scientist who has virtually made history in so many fields. When we were preparing for this, we became aware that Dr. Tunnicliffe was the first woman to be hired as a field assistant in what was then the Department of Geology and Earth Science. That department at McMaster University is now the School of Earth, Environment, and Society. And it's clear that Dr. Tunnicliffe, while she had her start at McMaster, went on to have and still has a fascinating career. How fascinating? Well, an interesting fact is that she has not just one, but 10 underwater species named in her honor. And when I mentioned this to her earlier this evening in preparation for this, she said yes, and some of them have very interesting names. I also heard that her personal favorite is a 3 centimeter long deep sea spider. So I'd love to know why that's the case. It's more fascinating to explore the fact that Dr. Tunnicliffe grew up in landlocked Deep River, Ontario, attended McMaster and Yale universities, and then has spent 4 decades unlocking the mysteries of the ocean. She has made hundreds of dives around the world and directed the development of the Venus Coastal Laboratory. Venus is located off of Canada's west coast and became the first cabled seafloor observatory when operations began in 2006. Now, I know what it takes to just even build a lab at a physical space on campus in a building, and I can't imagine what it took to build one on the ocean floor. This observatory is operated by Oceans Network Canada at the University of Victoria and still allows scientists to run and monitor ocean experience from their desktops back on shore. Very valuable, particularly during the pandemic. Dr. Tunnicliffe was the Canada Research Chair in Deep Ocean Research until her retirement in 2020. She's currently a Professor Emerita with the University of Victoria, and her research now focuses on deep ocean conservation, much in alignment with World Water Day, including environmental management and deep sea mining. In recognition of her scientific discoveries and pioneering leadership in ocean research, Dr. Tunnicliffe was named an Officer of the Order of Canada this last December. We are so very proud of you, and we are thrilled to have you this evening to return to your alma mater and be with us. I look forward to the lecture, and I'll turn it over to you now, Dr. Tunnicliffe.
Thank you so much, Dr. McDonald. I appreciate that. Okay, let me do the share screen thing. It is such an honor to be invited to speak to you today. I just love the thought that I'm back in Hamilton at McMaster, even if it's virtually. So I really appreciate this opportunity. So let's dive in. We do gain a huge amount from the deep ocean. We get food from the deeper ocean. And even if we aren't eating everything that's down there, there is a large amount of support of the food chains in the upper seawater as animals such as this lanternfish over here migrate daily from the deep water up to the surface at night to feed, and there they are feeding other organisms that we then capture. The deeper ocean is responsible for nutrient recycling. It also provides areas for protection and nursery areas for fish like these. We get pharmaceuticals from the deep sea, and also in climate change, absorbing heat and carbon dioxide from the atmosphere. Until now, there hasn't been a huge amount of impact on the deep sea. However, the pressures are mounting. We are now getting fish from deeper in the ocean. Microplastics indeed are everywhere. We dump our trash into the ocean, and that climate change, we are already seeing increasing temperatures and decreasing oxygen in the depths of the sea. And now the metals that could be found on the seabed are the latest thing to go after. In the areas of the high seas, there is one organization under the UN Convention of the Law of the Sea that can sign contracts for mining in the high seas, and that's called the International Seabed Authority. It has already signed 31 exploration contracts, and they are on a roll to get to exploitation with a timeline of less than 2 years. And yet the knowledge gaps that we have about this system makes it very difficult to predict what is going to happen. I began working in the deep ocean a while ago. So this is the submersible I was first able to use during my postdoc at the Institute of Ocean Sciences. I went on to be able to use manned submersibles such as Alvin in the United States and the French submersible. More recently, I've been using remotely operated vehicles. These are connected by a fiber optic cable, and our team helped to develop the world's first really good submersible called Ropos. But we've also used all of these systems here. The fiber optics allow us to connect to force feedback manipulators that collect things or do tasks on the seafloor. There's all sorts of collecting devices and measurement systems that you can attach. Send up the information to the ship where a larger research team can collaborate in the dive. This is my talk today. It's going to be across the Pacific Ocean. Now here you look at the seafloor, and there are many different terrains in which a variety of habitats can form, the lumpy seamounts and faults and trenches. The photographs I'm going to show you come from all of these locations that include Abyssal Plains sites. We have seamounts, and the stars are hydrothermal vents, my favorite, I admit. In the very top part of the ocean, this is where the sunlight comes in. It's where the largest biomass is. It's fueled by primary production in the top of the ocean. As we go deeper, things get darker. And it is here from the bathypelagic that we get these migrations that come up from the deep. In this little video clip, the light spots here are those lanternfishes that I mentioned. And here you see large Humboldt squid coming in to feed on these fish. The imagery was taken at night at about maybe 100 meters depth. And this is where the fish have come up and are feeding the surface. Now, below this is the Abysso-pelagic zone, which is actually the largest habitat on Earth, down to about 8,000 meters in depth. Down here, there's not nearly so many animals, but when you see them, you're taking photographs, jellyfish, salps. In the background, you also see these little white particles. When you look closer, this is what we call marine snow, and it's phytoplankton, zooplankton that have fallen down from the surface. And in this photograph, we also see the fecal pellets from zooplankton. Bacteria down here break up these particles, release nutrients, and the particles sink to the deep sea floor. And so this deep ocean is dependent on food from the sunlight zone, almost all. In the middle of the North Pacific Ocean, 4,500 meters in depth, a mud plain with all sorts of bumps and burrows and tracks in it. You can't see any animals here, but you dig in that mud and it's just full of a riot of diversity. What these guys are doing is digging in that mud for the organic material. So any small change at the surface of the ocean in that primary productivity is really going to affect these animals. In other parts of the ocean, you can very quickly find the big eating machines. These are sea cucumbers in Indonesia that are eating across this abyssal plain and excreting the mud out the other end, trying to strip the organics. Here is another sea cucumber that we kind of frightened and it took off, depositing its load. Many sea cucumbers can swim, and some spend a lot of time in the water. This sea pig has come down, done a face plant, taken a gulp of mud, and here you see it swimming up through the water with the sediment in its gut that it will then deposit somewhere else. In Indonesia, we also took this incredibly rare photograph of a meter-long acorn worm, which is a supreme processor of sediments. You can see this wonderful fecal trail behind it. The abyssal plains are also the host to polymetallic nodules at very specific sites. Now, these manganese nodules, I'm just holding one up to the camera here, are potato size, and they are of particular interest because of the nickel, cobalt, copper, and manganese that are found. So as I mentioned, the International Seabed Authority can let contracts for mining nodules such as this. The key area for manganese nodules is in this swath from Mexican waters to just south of Hawaii in the high seas. And these polygons colored in here are the contract areas for exploration for nodules. Mining has not quite yet started. But you can see it's a very large area. This is also a very hard area to access. There's been very little work here until just the last few years. It has taken 30 to 40 million years to form these nodules. Now, they're on the surface because it happens to be an area of the ocean in which there's almost no productivity in the ocean surface, so the nodules don't get buried. There are animals that live here. They've also had a very long evolutionary time to adapt to these conditions. And the animals here that are dependent on these nodules are unique to this area. This is the scenario for mining these nodules, in which a large machine will go across the surface, raking up the nodules into the machine, and then a slurry will go up and be pumped up 4,000 to 5,000 meters in depth up to a ship on the surface. The ship will dewater the load and send the unwanted residue back down into the lower water column. This is a prototype built in Belgium. It's about a 1/3 size with a man sitting beside it here. Now, in this image below here, this is an idea of what it might look like as those several machines go across. And you can see the big sediment plumes that are being picked up in the water. Now, you remember I said this is very, very clear water. There's nothing in this water. And this is one of the big concerns, is what is that sediment plume going to do to the rest of the area? To make this profitable, a mine must be about 25 to 30,000 square kilometers, about 1.5 times the area of Lake Ontario. Well, does this ecosystem matter? There's lots of abyssal plains, but most do not host manganese nodules. This is a specialized habitat in restricted areas. The mining impacts are not just going to be limited to nodule removal. I've mentioned the sediment plumes, but also there's concern about toxins that will come back into the water column, into the food chain, and what that returned waste is going to do. Frankly, we simply don't know what the ecosystem linkages are from these abyssal areas to the rest of the ocean. How will that affect carbon burial, for example? Here's one example of an ecosystem service. We have a sponge stalk attached to a manganese nodule, and this small octopus is laying her eggs on the stalk of the sponge. Okay, let's go to seamounts now. We've gone to the west coast of Canada, and this red area off Vancouver Island depicts an area of interest, which is the first step for the government of Canada to make a marine protected area here. The black triangles are seamounts coming near the surface, and the yellow dots are hills on the seafloor. Now, Fisheries and Oceans has a lot of wonderful videos of what these look like. So if you just go to the DFO website and search on videos, you'll find them. It's really worth it. These seamounts near their summits foster dense areas of glass sponges, of corals, and these are all photographs in Canada. There is enhanced productivity around the tops of the seamounts, and this attracts many migrating animals and areas for fish such as this pregnant rockfish to come and lay eggs and the young to grow up. These are also way stations for migrating species such as birds, humpback whales, even the great white shark. The reason of concern recently about seamounts is because fishing is such a concern here. This is a seamount I visited in 1982, and then DFO went back 30 years later. It didn't look anything like this. It was covered with discarded nets and lines, still ghost fishing. The corals in the area have been wrecked by the trawls. Corals and sponges are just really important foundation species. They sponsor so many other species in their branches and in their interstices. They are probably the world's oldest organisms, dating up to tens of thousands of years old. In this video of a seamount just south of Hawaii, you will see the corals and the animals that are associated with them, such as these brittle stars. They like to get up off the bottom so they can get into higher currents and pluck food out of the water column. Many different species. In this wonderful shot, I like to call these Dr. Seuss sponges. They're all lined up in the current. These are glass sponges that are very old. Now, if you look at the lumpy, bumpy surface that they're sitting on, that is called a cobalt-rich crust. Cobalt-rich crusts form in the North Pacific. It's a crust maybe up to 20-25 centimeters thick and rich in cobalt. And it's characterized by this crust that covers the basalt. And again, here's a scenario of mining forming on the summit. It's going to crunch up the crust, going across the summit, and then pumping the slurry back up to the surface again. Of course, taking everything else with it. In the North Pacific, the thickest crusts are in the Northwest, and there are 4 seamount contracts that are signed for exploration in this area. As we move to hydrothermal vents, these are associated with areas where there may be heat release from the ocean crust. The red symbols represent areas that we know are active hydrothermal vents. The yellow are presumed vents. And these are forming in mid-ocean ridges, for example, but you also have volcanic arcs that have heat release. And in the back arc area, there's also small basins with spreading. Now, there is also interest here in mining. And for the international waters, this would be in the Indian Ocean and the northern mid-Atlantic ridge. But there's also deposits that form in national waters. So there are exploration licenses that are given from several nations in the Southwest Pacific. And Japan has also trialed mining in its own waters. Where you have heat underneath, a magma chamber, you will find areas which can foster hydrothermal vents. And here magma has come out on the surface just near Canadian waters. This was just a couple of months before the photograph was taken. And that seafloor is very leaky. So seawater penetrates under that seafloor crust. It gets trapped, it travels deeper and deeper, and it begins to heat up. And as it travels, oxygen is converted to hydrogen sulfide, and minerals and metals are dissolved from the deeper crust. When the water becomes superheated, it rises quickly, comes out at the seafloor, and hits the cold seafloor, and that's where it deposits its load of minerals in combination with hydrogen sulfide. Sometimes there's cooler water that cools that hot water off, and you'll get more diffuse flow coming out that's also rich in hydrogen sulfide. The hottest water that's been measured at hydrothermal vents is actually in Canadian waters, the Endeavour Hot Vents area, where 400 degrees is measured. And here we see the chimneys that are deposited by that hot water and the smoke, which is particles. This is a brief video from the Gulf of California, where you can see the water is just jetting out, hitting the cold seawater, and then forming the smoke particles that are rich in metal sulfides. But the other fascinating thing about these emissions is the process of chemosynthesis. So here we are looking at the side of a chimney. There's warm water that's coming out that's rich in hydrogen sulfide. There's oxygen in the deep sea water. So when you put oxygen and hydrogen sulfide together, you get energy. Now, there are microbes that are capable of capturing this energy and mediating it inside their cells so they can get the energy. Once they have the energy, they do just as plants with sunlight energy. They take carbon dioxide from the water using the same enzymes as plants, and they convert it into organic carbon. And then they grow like mad. And that's what, in this case, this furry white stuff is filamentous bacteria. But there are many, many kinds of microbes that do this. As such, they also foster an extended food chain, such as these lovely deep sea spiders that eat the filamentous bacteria. We have snails that graze bacteria, and then polychaetes that are feeding on the animals, crabs that are eating the snails. So you get a full food chain developing, fueled by in situ chemosynthesis. There are many different types of symbioses with these microbes. For example, these orange spots in this image are the plumes of a worm, and it builds a tube, a lovely lacy tube, where the bacteria grows, and it comes out of its tube and it eats off the bacteria. This barnacle, found only at hot vents, puts its cirri out into the water, grows the bacteria, pulls it in, eats the bacteria. And the shrimp do the same thing with their mouth parts. They grow bacteria on the mouth parts, then lick it off. And the ultimate symbiosis is to take those bacteria and put them right inside you. Just don't worry about trying to grow them outside. And that's what these clams found at hydrothermal vents do. They have no gut. Instead, the bacteria are symbiotic right inside their cells, and they use hydrogen sulfide as the energy source. It's able to sponsor really high biomass at these vents. In this video from East Pacific Rise, we see fish swimming around at this hot vent over these clams. As we zoom in, you can see the siphons here that are taking in the carbon dioxide and oxygen into their gills, but the foot that is down in the crack is picking up the hydrogen sulfide. And that is then delivered by the blood system to the bacteria. Now you'll notice these gills are pink, as are the fish. That's hemoglobin. Hemoglobin is extremely good at capturing oxygen, which is pretty low in these waters. And here it is, bright red, hemoglobin in the giant worms. These are polychaetes that are highly modified. They have no mouth, no gut. They just use their gills to pick up the three gases, H2S, carbon dioxide, and oxygen. And so they pick this up with the gills. These are worms found on the Canadian hot vents. And here we are off Mexico. It's a different species. And they're feeding their symbionts, which are down beside the big tubes. This off Mexico, this is a chimney, no longer venting really hot water, but rather about 25 degrees C. And you'll see the biomass. These worms are about 1 meter long, and it's just enveloping the whole chimney. So again, they're taking up the gases and using the blood system to pump it down into a specialized organ inside called the trophosome that is filled with bacteria. And it's kind of like a giant blood sausage. These are the foundation species for this ecosystem. The clams, mussels as well, the tube worms, they are supporting crabs, fish, and many other species. And here you see just covered with limpets. We've got some polychaetes. All these are polychaete worms into the final higher end predators such as this octopus. Here is, we're collecting mussels also with symbionts inside. This is on a seamount in the Mariana Arc. I'm trying to collect just with these collections were the entire master's thesis for one of my students. You can see the manipulator arms of the ROV, just trying to get the last mussel into the bag. So that's my student's thesis. These mussels are living in an incredibly low pH. This pH here is down to almost pH 5 from an average ocean near the surface of 8.3. The mussel shells here are incredibly thin. It takes nothing to break these shells, but they have many adaptations to this setting. In this photograph, you can hardly even see the worms here because the temperature is so high. They live at over 50 degrees almost all of the time. There's almost no relief from that temperature. Tremendous adaptations to these extreme conditions in physiology, in behavior. Every hydrothermal vent we go to, they're new species, and it's a real task to find the taxonomists to help figure out what they are. Globally, about over 900 new species have been collected. So what have hot vents ever done for us? Well, the discovery of hot vents has been incredibly important to understanding the origin of life on our planet. By delving down into these microbes, the archaea, the the new metabolic pathways that are really simple. People have begun to understand how life could have actually originated, and probably in conditions like this on our planet. That is driving exploration for life in the rest of the solar system. We're understanding more about adaptations to extreme conditions, such as protein folding to protect against high temperatures. There's several biopharmaceutical products that are coming out. That chewworm hemoglobin, for example, is being looked at for its extra binding capabilities and helping in surgery, for example. And here, this marvelous piece of art, just inspiring artists with ideas of worlds that you suddenly realize are on our own planet. But this hot water also deposits metal-rich chimneys. You take a cut across a chimney like this, and you see copper, nickel, zinc, gold in high concentrations. There are machines that have already been built to start mining, and these are two men here, so it gives you a size of what will be operating on the seafloor. This is where there's a mining license that is signed with out of Tonga, although it's not active at the moment. At the top of a volcano here, there's a crater, and this large area across here is all sulfide ore that is deposited by hot water. In this image, we're flying around one of the chimneys here. It's not venting high temperatures anymore. That's originally what formed it. We've got a long-nosed skate that's flying in here to investigate what we're doing. The orange color is due to iron oxide that is forming on the outside. And here you can see large snails that are occupying much of this. These snails also have symbionts inside them. Well, can't we afford to lose a few of these spots to mining? What we've realized is that each one of these sites is tiny. It might be the size of the floor of my house. It might be the size of just my living room. As we add up the areas going around the world, globally, we believe the total ecosystem is less than 30 square kilometers. Add to that, 80% of the species that are known from this habitat are known nowhere else. And many of them are so novel, they have no close relatives anywhere else. In addition, if, say, you look at the vent fauna in New Guinea, you won't find the same animals down near New Zealand. You certainly won't find them on the Juan de Fuca Ridge. So they're highly regionalized. It's pretty clear that removing this habitat in any one area will mean extinction for someone. There is a strong move to conserve in some countries. Indeed, Canada was the first to put hot vents into a marine protected area, followed subsequently by Portugal, and then Mexico. The United States has protected the hydrothermal vents near Guam, and recently New Zealand as well. However, we are projecting that we need metals to fuel the green energy that we're pushing for. And that needs metals such as nickel and cobalt. We know that several deposits on land appear to be poorer and poorer grades, although there's some argument about that. Cobalt and rare earths supplies are dominated by China. And we certainly know that land mining has many environmental issues. Thus, there is a strong push down to the seafloor. However, one might ask if we're just prolonging the inevitable, that we can get maybe a couple of decades, we can get metals, but then we'll have the same problem. So maybe we need to be searching for those battery alternatives now. Maybe we can do something about negotiating our supply chains better. And certainly we can do something about more responsible environmental impacts on land. The problem is that our knowledge is totally inadequate to predict what's going to happen on the seafloor, and we certainly have little capability to monitor it. We do predict, however, that habitat removal will mean extinction of some species. There is a counter push to impose a 10-year moratorium until we know better. So what can we do about informing the decision that is going to be made? And what happens in the International Seabed Authority will affect what happens in individual states. Here's a photograph of the council meetings at ISA headquarters. And there is a council meeting happening right now this week as the push to make this happen is now stronger and stronger. The NGO to which I belong, as other NGOs, we are trying to deliver science information to the voting delegates here. I've been at this meeting as an observer, as have my colleagues. We present policy briefs, we give presentations. And now we're finding, as I heard yesterday, more countries are questioning the environmental issues that are being raised, especially by the NGOs. And we are seeing some moves to recognizing that there should be protection for active hydrothermal vents, although that has yet to happen. We and others are commenting and trying to change ideas about the regulations for exploitation and how they will be managed. We're directly working with the Canadian delegation who's sitting over here. Canada has a seat on this council and is influential. But again, we ask, why can land mining not do better for terrestrial ecosystems so we don't have that excuse to go to the seafloor? So every time we go down, there's so many discoveries, so much left to learn in this ecosystem where 95% of the Earth's biosphere from the twilight zone on down. There's a huge habitat diversity with many novel adaptations to extreme settings. Can we afford what we're proposing to do? And as we go deeper, it just seems that we really need to get more information to inform better and better stewardship. It's our future generations that will need a functional ocean. And just to echo, as Dr. McDonald started here, a really important aspect is equitable access and listening to Indigenous peoples across the globe about what the ocean means to them. So in ending, I want to thank you again for this invitation, and a special thanks to my alma mater, to the departments of biology and geology, but especially to my undergrad supervisor, Professor Michael Risk. He hired me at the beginning, sent me off to Bay of Fundy, and had some sort of faith that I would do something. Well, I did. And from the mudflats, I just kept going deeper. And so with that, I'll end. Please just take a look at what it takes to get into the deep sea, so much funding and support that is necessary. And thank you very much for listening.
Thank you very much, Dr. Tunnicliffe, for sharing your insights and experiences with us. Excellent talk, great videos, fascinating stuff you have done. Thank you for your efforts. Thank you for your dedication to this area that is so important for our environment, Earth. So now I would like to open the lecture for the questions. If you have a question for Dr. Verena, then please post it in the QA box there. So I will start with questions. first question is, when the ocean is in the country's boundary, then the country is responsible for in the inner areas, who is allowing the mining and how the regulation work? Is there regulatory authority and how it can be?
Yes,
regulated?
and different states, of course, have different regulations. And many of them have no deep sea mining regulations, so they're trying to develop them in this instance. But once, if they're a member of UNCLOS, the UN Convention of Law of the Sea, and the International Seabed Authority sets regulations, states are bound to at least meet what those regulations say. Now they can impose more. Now Canada doesn't have deep sea mining as such. They do have regulations that govern oil and gas exploration and exploitation. So one could see if it ever happened in Canada, which is unlikely, that would be the agency that would take that on.
Okay, thanks a lot. And then you have discovered many new species. So any guess how many species might be there, and our understanding of the number of the undiscovered species?
In the deep ocean, well, the conservative estimate is probably around 30,000 species. It's very, and many of us feel that's truly conservative. So probably just because just in the last few years, people have been exploring these manganese nodule areas, and it's overwhelming. We're being pushed to try and inform the regulations when you're facing everything's new. You take another grab of mud. So I suspect those numbers probably near 50,000 to 100,000 new species in the deep sea. Who knows?
Yes. So then the other question I would have is how, what do you feel is the largest and the most damaging human threat to the ocean ecosystem can be? You have mentioned mining, so can you elaborate more on that aspect?
Biggest threat, however, I mean, I'm on a roll with mining at the moment because so few people know about it, but it's climate change, because that's affecting everything. And it's climate change because the ocean is taking up nearly all of the heat that we put in the atmosphere. And the temperature change is just, that is what is going to really kick things. Temperature heating up at the surface, we all know what's happening to coral reefs, but still you heat, in Canada, you heat the surface and the ocean can't turn over as well as it did. That means that the surface, you're getting plankton blooms, that's falling down. The bacteria are using up the oxygen. So the deeper ocean is suffering from hypoxia and oxygen loss. And meanwhile, it's taking up the carbon dioxide and you're getting ocean acidification. That is the thing we have to address first and foremost.
Okay. Yeah, that's very, very important point, because the whole system will be impacted rather than the localized impacts of the mining. And then for the citizen, the listeners, if people are listening at their homes, then what can be implemented to alleviate these threats? First, that comes to the mind, okay, what we can do to address this?
Well, again, you know, you think about the Canadian energy footprint, and I don't need to tell you, you know, what can we do individually to diminish our CO2 emissions, whether it's cars or I'm changing all the windows in my house because that'll make a difference. And I think there's a lot of information known on that, but also sustainable seafood. Next time you buy a fish, ask where it came from, how was it fished? Most of us in British Columbia really try hard to only go for things that are either trapped and not trawled, so you're not destroying the seabeds. Are you long lining rather than using big trawl nets in the open ocean? So that's another thing that you can do.
Okay, Okay, so the one question I have to ask is from Dr. Mike Risk. So when you were doing the research, did you see any pH excursions in the deep sea and how it may affect the creatures and the shell species there? It's from Dr. Mike Risk.
Oh, yes. And he's very interested in corals and acidification. I know that. The answer is no, and that's because our instruments are not good enough. Our instruments are not, to be able to leave in the deep ocean, you've got difficulties with pressure and the chemical reactions. And I've run an observatory. We've tried really hard to put pH meters on the observatory, and the engineering is getting there, but it's not there yet. What I did mention in my talk is working on a site where the pH is incredibly low. And on that particular volcano, well, there's hot vents, but there are also other animals living on that volcano. No corals, you don't see anything that needs calcium carbonate. So pH diminishment in the ocean really is a threat to anything with a shell. And so it happened to be amazing what this particular mussel was doing. And we were using that as an idea for what might happen to other systems as pH goes down in the ocean.
Yes, that great. And then the other question is that how would any regulation or moratorium can be enforced? Are we moving towards that at an adequate speed? Because sometimes the international negotiation can take decades.
Yes.
What are your thoughts?
The only way that mining will, the only way that's going to happen at ISA will not accept the word moratorium. And apparently there's a legal reason under UNCLOS. And the only way it's going to stop going for mining is if in the next few months, the countries that have to vote on the regulations to go forward don't say yes. And there is it's actually quite a high level. I believe 66% have to disagree. So it's a really tough thing to negotiate. What I suspect is going to happen, right now, there are still many, many questions just this week coming up about the environmental regulations and the financial regime. So we're supposed to be mining this seabed for the benefit of humankind, and the profits from mining have to be shared equitably, especially with developing nations. So if you can imagine the difficulty of negotiating what equitable sharing means and how much royalties is to be paid. And again, this week, I heard that there is a lot of disagreement. So this is the likely thing that may slow things down, is lack of agreement that will allow all of the regulations to fall into place at one time. As time goes on, there seems to be more and more awareness in the delegates, which is great. And so more and more questions being asked. And I'm just hoping it does slow down so that we can get those regulations as well. I don't even know how we're going to monitor what happens. We can't, this is out of sight, out of oversight. And at least on land, we can see what an open pit mine is doing. There's no way we can see what's going on under the sea. So I don't want to lose hope. We still keep working on, if it does happen, how do we do it the best we can? We'll see.
Yes, thank you. I think that's a wonderful message from you at this point. I would like to bring our talk to close. And then again, I would like to thank our partner, McMaster Alumni Association, and especially to Karen McQuigg. Our special thanks goes to the team who has worked behind the scene running this event, especially to Jessica Lunsbury, Dawson Owen, and J. Rob. And thank you, Dr. Verena Tunnicliffe and Dr. Maureen McDonald for being with us tonight. To find more about McMaster Center for Climate Change, please visit our website, climate.mcmaster.ca. Thank you and good night. Thank you very much.